Okay, so let's look at one last example on optimization. Let's say we have two corridors that meet at right angles. Okay, so this is a right angle. Here's a right angle and here's a right angle. And this is a corridor. This is a hallway, this is a hallway. And they're 2 meters and 3 meters wide respectively. This one is 2 meters wide, 3 meters wide. Theta is this angle right here. And AB is a thin metal tube which must be kept horizontal. You can say maybe parallel to the floor. Okay, if you think of this as the tube must be kept parallel to the floor, that might make a little more sense in this. It's kept horizontal and cannot be bent around the corner from one corridor to the other. So think of it as there's a man picking this side and there's a man picking up this side, and they're trying to walk through this. Okay, so I guess you could, if the pole, the thin metal tube, has to be kept parallel to the floor at all times. Okay, so think of it like that. It could be either flat on the floor up here, or it might, you could keep it flat to the ceiling. Okay, but it would have to be kept. It would have to be touching this corner. Okay. So show that the length of AB, show that this length is given by L equals 3 over cosine theta plus 2 over sine theta. Okay, so let's think about that. After you find that, show that the rate of change of L with respect to this angle is 0 when theta is 41.1 degrees. Okay, so let me redraw that so it's a little bit clear. 41.1 degrees. Okay, and then part C says find L when theta is this angle, and comment on the significance of this value. Okay. All right. So I have a tube AB. I'm going to try to move it through this corridor, through this hallway. But when I get to this corner, okay, it must be kept straight, and it must be kept straight. Okay, so that's kind of what's happening here, isn't it? Okay, but the question says, well, what's the length? How is the length going to change relative to the angle? So if I make this angle flatter, you would expect the length to be longer. If I make the angle steeper, you would also expect it to be longer, right? Okay, so if we can maybe find the derivative of that, right, we can see that there's going to be some kind of change here. A and B always have to be stuck on these walls, and this point must touch. Okay. You can see that there's going to be some kind of relationship between theta and L. Okay, so let's think about what L is. So L is the length of AB, and we can say L is equal to really A plus B if I define A to be this segment and B to be this segment, right? We also know that this angle here is going to be the same as this angle, as long as this line is considered parallel to this line. And since this is a right-angled corridor, we would expect this to be a right angle, okay, as well. And so this would be parallel to this line, and we can assume that this line is parallel to that line as well, okay? Now, if I look at this triangle separately and this triangle separately, I'll be able to find a relationship maybe with A and an angle, right? B and this angle, and maybe combine those to form L. So let's look at this first triangle here. This is really cosine of theta. Okay, if I start from this angle adjacent over hypotenuse, and this angle is sine opposite over hypotenuse. Okay, so once I have these two relationships, I can rewrite these. Cosine of theta and A switch places, so A is 3 cos theta, 3 over cos theta, B is then 2 over sine of theta, likewise, okay? And now I substitute these into my original equation, my original relationship, and I end up here, okay? Notice also that theta must be between 0 and 90, okay? Once I start going past 0, I'm going to end up with this long metal tube starting to go into the wall, which doesn't make sense on this side. And if this goes up to 90, this tube will start going into this wall over here as well. And plus, the tube would get ridiculously long if the angle gets really, really steep, close to 90. Okay? So, now we have to find the derivative of L with respect to theta. And that shouldn't be too hard. Okay? Let's look at, since we know L looks like this, if I can write it in a form where we can derive it, then we're okay, right? So let's bring the cosine of theta up to the top and sine of theta up to the top. And then I end up with L equals 3 cos theta to the power of -1 and 2 sine of theta to the power of -1. If you wanted, you could write this as a secant, and you could write this as a cosecant, but you know, that's not necessary. That's not really necessary right now. Plus, it might make the derivative more messy. Okay, so let's see. Just as a note, side note, this is not the same as the inverse. Okay, this is not the same as the inverse. This is a reciprocal of cosine, and this is the inverse of cosine. So please remember that as you do this. Once I derive that, I end up with -3 times, by the cosine rule, okay, that becomes a minus, or sorry, not the cosine rule, sorry, the power rule, -3 times the cosine of theta to the power of -2 times the derivative of the inside, which is the chain rule, which is this chain rule, and so we end up with times negative sine theta and -2 sine theta to the power of -2, okay? This -1 comes down to the front, and that becomes -2. Then I take the derivative of the inside and multiply it to the outside, okay, and that becomes cosine of theta. From there, I can, if I rewrite this so that this is now a positive exponent, I bring those down to the denominator, and then I add. If I combine these two fractions, I end up with this. Okay, notice that I'm doing 3 sine theta times sine squared theta, and times sine squared theta over sine squared theta, and to this term I'm doing times cosine squared cosine squared theta over cosine squared theta. Okay, so I end up with this expression here, and so that would be my dl d theta. Okay, I probably can't simplify this much more. Okay, now when is this equal to 0? Because that was our question, right? Show that this is equal to 0 when theta is 41.1 degrees. So I'm probably going to set this equal to 0 first and then end up with solving for theta and coming up with this expression. That's my plan here. So if I set this equal to 0, that makes the numerator, that means the numerator must be 0 when this is 0. And so we set the numerator equal to 0, and we can solve from there. You can see that if I bring this term over to the other side, I end up with that. I now divide everything by cosine cubed to get tangent cubed, divide everything by 3 to get 2 over 3, and then take the cube root of both sides. Notice it's not plus or minus because that's an odd power, and I end up with the cube root of 2/3. And then I solve for theta, which is the inverse tangent of the cube root of 2 over 3. And that on your calculator in degrees will result in 41.1 degrees. Okay? Now, find L when theta is this angle. Okay? And then comment on the significance. So all I do now is once I find this, I plug it back into my L formula, L of theta. I put 41.1 in here and 41.1 in here, and then you use just your calculator basically to solve this, okay? And you end up with L equals 7.02 meters. Now what does this mean? what does this angle tell me? This angle tells me either the minimum or the maximum, doesn't it? Okay, it tells me that either the minimum or maximum value angle, where or the angle, sorry, where L is going to be a maximum or minimum. So in order to interpret it, I need to really be looking at the sign diagram. Okay, so let's look at the sign diagram of DLD theta. Okay, I know it's going to go from 0 to 90, and my critical point occurs at 41.1, and then I plug in numbers. Okay, so you could plug in, for instance, 30 degrees, since cosine of 30 and sine of 30 I should know, cosine of 60 and sine of 60 I should know as well. But you could use your calculator for this, okay? If I plug in 30, I'm going to end up with this expression becoming less than 0. And if I plug in 60, this becomes greater than 0. So I end up with a negative on this side and a positive on this side. So my graph of L is a minimum, okay, at this point. So what does that tell me? What does that tell me? That tells me that when my angle is 41.1, L is going to be the shortest. Okay? L is going to be the shortest length. Okay? So this length is going to be the shortest, where it's constrained so that this must be touching and B and A must be touching the walls. If I move my angle any more, if I make it any bigger, my L is going to increase. If I make it any smaller, my L is going to increase. Okay? So what does that really mean in terms of if I was to move this, if I was having to move this through this corridor, what would that mean? That would tell me that this is the longest rod. Okay, this is any rod that is longer than AB, any tube that's longer than this current length at this point of 7.02 meters would not be able to fit through this hallway, basically. It would get stuck. Okay? So the longest rod that can move through this corridor is one with a length of 7.02 meters. Okay, and I hope you can see that. Okay? If this rod is any longer, it would get stuck because the length of L, it would probably get stuck before this point, right? If theta was smaller, it would get stuck probably right around here. If it was any bigger, it would probably get stuck right over here. Okay, or even before I make that turn. Okay, but if it's exactly this length, then it will just be able to squeeze by. Okay, so hopefully that makes sense. All right, and if you have any questions, please let me know. One note, when you do these problems, make sure that you are using your calculus techniques as much as you can. It's okay to use your calculator to find zeros, but you should be using as much calculus as possible. Okay, for instance, using sign diagrams or concavity tests. All right.